I was part of this guy, and with those menu, I was like, oh, commercial. I even have yeah, they're way back. Yeah, what did you get? And you went to the that one. Yeah. Wow. Wow. It's like a signature. Yeah, that was a creepy part. I can tell you the legal website. Not like they have like I don't know any model rock. Oh yeah. No, people got down. Yeah. Sometimes I do. Yeah, you gotta make it dumb. I can't get too much. Exactly. One time I ordered at like the fast food but they didn't really give me the guy like go do it, go make it yourself. Scale out the competitors. Yeah. It's just we have to as you go up in size in context. So what about the three? Oh, actually, the colors. It's actually very effective. Okay. Yeah. I mean, obviously, like sure. So then you get it. So we all have to share the we will take. Yeah, you can take future. I think you're not many. You can figure out with whether you or so the ceiling left. Wide over the eye, don't because the feeling against my students are here. You hear for like 1 more week, he's having on. So I'll be mentally think of this part. I think of like the local. He's going to Greece for this. I agree. To the waiting. Yeah. You know, I have for accommodating also convenient that there's like daycare has like a terms they have extended hours. Pick you up, drop you off, and take you wake up. Even hourly. Wait until
Cool. There's more seats in the front row if anyone needs one. Cool, and I'll get started. Thanks everyone for coming today. Probably heard that I'm hosting along with Yun Tian and Victor, Professor Kyunghyun Cho, who I am honored to have the ability to introduce. So I want to start by quoting Cho's own social media profile, his own bio, his own words. He called himself a mediocre combination of a mediocre scientist and a mediocre advisor, which is to say he's the most humble person you will ever meet in your life. In reality, he's the Glenda Rice Professor of Health Statistics at NYU, where he's a professor of computer science and data science. He is the co-director of the Global Frontier AI Lab alongside Yan LeCun, and the first of many Canadian links. He's also a CFAR fellow in the Learning in Machines and Brains program, CFAR, of course, being the Canadian Institute for Advanced Research. It's the understatement of the year to say that he's a leader in ML and NLP, as I'll mention a contribution or two in a sec. He did his bachelor's in KAIST in South Korea, where he grew up. And then he did his master's and PhD in Aalto University in Finland. I'll mention his PhD year was 2014, 12 years ago. I emphasize that because he's done stuff in the subsequent 12 years, which I think most people can hope to do half of in their entire career. It's really remarkable. In particular, that same year, he finished his PhD. He came to Canada, actually. He was in Mila in Montreal working with Joshua Bengio as a postdoc. And that first year he was there in 2014, he co-invented what's known as attention. So if you've been living under a rock, attention is pretty much the key technique which has been fueling all these large language models. You can draw pretty much a straight line from his paper back in 2014 to all the things we see nowadays. After his postdoc, he started at NYU as a professor where he'd been for the last decade. And he basically speedrun every major career accomplishment you can imagine in that time. For example, he has PC chaired all three of the major conferences. I'm not sure if anyone else has actually done that at all. Do you know?
Maybe Alex.
Maybe. But yeah, he did NeurIPS, he did ICML, he did iClear. I know nobody else has also co-founded a journal. He co-founded TMLR, Transactional Machine Learning Research, which is in like 22, I think, and it's really grown in popularity. And
Yeah, when will you make the next conference?
yeah, we were talking about this the other day. We'll chat more later. We can do this. Besides that, also in 2021 he co-founded a startup, Prescient Design. In 2021, he sold that startup to Genentech, where he also spent some time as research. So he's done it all: research, service, entrepreneurship, everything. What he's also done is a lot of philanthropy as well. So let me still talk about research accomplishments. His biggest prize is certainly the Samsung Hoang Prize in Engineering, which is kind of one of the highest honors you can imagine in Korea for scientists. And unlike some of these awards where they give you a firm handshake and a pat on the back, here they give you a lot of money. They give you 300 million Korean won, which is on the order of 300,000 Canadian dollars. Still a lot. While maybe some of us would go and blow that on Lambo, Cho did the exact opposite. He gave back in enormous ways to many different institutions. For example, he gave 100 million won, or about $100,000 to KAIST to support women in computer science in honor of his mother, who was an undergrad at KAIST. He also gave 100 million won to Soonsil University to support Korean literature and arts, where his dad was a professor. And he's given somewhere between $100,000 and $200,000 to institutions like Aalto University, where he did his PhD, as well as in Canada, Mila and CFAR, just to support students and research and things like that. I'll mention many of these were before he sold his startup as well, so it's even more generous at that stage. He's also a co-donor of Open Review. I'm sure many, if not most of you have used. It's kind of where all the ML conferences are hosted. It suffered a cyber attack in November of last year, and he, along with a number of other donors, co-donated $1 million to it. I don't know how much exactly. It's a small amount, though. I had $101. You probably did a little bit more than that, but judging by past numbers. On top of all this, he's just really a kind, warm, really funny person. It makes you forget that you're talking to such a brilliant scientist when you have a conversation with him. So, without further ado, Professor Kyunghyun Cho.
Thanks for the super generous introduction. I mean, I didn't need it Lambo because I live in Manhattan. I'm not even sure where I'm going to park it if I had it. Yes. Um, Anyhow, despite all those things that Gautam said just now, I'm going to talk about something that has nothing to do with all those things, and something that I've been actually thinking a lot about on side of the research at university. And there is a kind of causality, and then how we should think about, or how started to believe we should think about it from the perspective of the machine learning and the large scale machine learning that is deep learning. I'm going to spend some time on kind of motivation behind what we need to think about the causality nowadays. And then I'm going to talk about the causal discovery, causal estimation, and then finally, very latest kind of study that we just conducted and finished on the causal identification as well. But the latter three are kind of, let's say, the very natural, let's say, follow-up. So let's start with the motivation. And then there is, of course, this kind of a very obvious topic that we all talk about, but then they often forget when we actually start building this kind of large-scale models. There is indeed some difference between correlation and causality, or the causation. So let's just think about this phrase, correlation does not imply causation. And we actually run into this kind of phenomenon over and over. So for instance, there is a uncanny correlation between the distance between Neptune, the planet, and the sun, and the air pollution, the level of the air pollution in Washington, D.C., United States. Is actually ridiculously well correlated there, in particular if you look at this particular duration. And then, of course, looking at this one, we know that yes, there is a correlation, but there probably isn't a causation there. It's not like we're going to improve the air quality in DC further by having Neptune won't approach sun any further. It doesn't make any sense, right? And then also making the DC's quality, air quality better, it's not going to make Neptune get closer to the sun either. So this is a kind of, let's say, obvious kind of, let's say, example of the correlation does not imply causation here. And then why does it happen? That's just because we forgot to take into account this confounder that is a time. So for instance, 1980s where US started to seriously think about the environmental, let's say, effect of the air quality as well as various other, let's say, industry. And then you had it turned out, in fact, okay, so it turned out that the cycle of the Neptune is about 164 years. And then how many years has it been since the 1980s? It's been about, let's say, 45 years or so. So it just happened to be like that. That is because of the hidden confounder that is effectively time in this particular case. But what is really interesting is that it's actually not useless, right? So it still allows us to make some prediction. That doesn't allow us to act on the word, but it allows us to make a prediction. And then this really tells us about the kind of, let's say, how we should approach the correlation versus the causation. The correlation doesn't imply causation, doesn't imply that we should just ignore the correlation because it's still very, very useful. Now, another typical example that we see is this the picture of the places of a fighter jet that has, well, not jet, I guess, anyway, fighter jet that has been hit by the enemy guns collected from the World War II, I think, if I recall correctly. And in this case, you can imagine that the fighter jet came back, and we see that those are the places where the jet was hit with the enemy bullets. And then we might actually decide incorrectly that we're going to reinforce those parts where the enemy bullets actually hit the plane. And then without realizing that, in fact, we never actually got the plane come back when they were hit in the engines, right? It doesn't make any sense. So this is another example of the correlation does not imply causation, and then thereby it's really difficult for us to actually make an action recommendation or to decide what to do about it based on the correlation alone. And then it really requires us to have some kind of theory behind what is happening in order for us to use the causation to make a decision. But nevertheless, the prediction is still, or the correlation is still very, very useful. Because what are we going to do? Based on this correlation, right, that doesn't allow us to take an action, we can still prepare a lot more of the, let's say, spare parts so that we can fix it much more rapidly and much more quickly than before. So correlation does not imply causation, but may facilitate prediction. And then this is exactly how the whole, let's say, field of the deep learning has been successful. Is that by capturing all possible correlations that is available out there in the data, we can make a prediction. And then these predictions can be very, very useful for many different applications. Not necessarily, however, for us to change the world. As soon as we take an action that's going to change the world, a lot of the predictions that are made based on the correlation will break down, and then they're going to become invalid. Thereby, we can't really make take any kind of action based on the correlation-based prediction. And then it's really a kind of a clear thing, and then this is what everyone was saying. But usually, we tend to decide to stick to one of these two. Let's say either studying about the correlation or the causation, and then just go deep into each one of these aspects. But of course, we need to think about both of them all simultaneously. And then of course, I just given 2 examples, but these examples exist, there are like infinitely many of them. So another example is this. There is a amazing correlation between the number of movies Emma Watson appeared in and the votes for Democratic senators in Michigan. And it's a kind of a weird correlation. I don't even know what goes behind this as a correlation. There must be something that I just cannot think of. And then this really tells us a lot about the world, but also at the same time tells us a lot about what we don't know. But again, using this kind of correlation, we are going to be stupid to act on the world based on this correlation. It's not like, let's say I'm a big fan of Emma Watson, so thereby I'm going to move to Michigan, and then they start voting for the Democratic senators. It's probably a bad idea in general, is if my whole sole goal is to increase the number of movies Emma Watson appears in, and vice versa, right? So I'm not going to invest in this kind of movie studio so that they can actually hire Emma Watson to appear in the movie because I want the Democratic senators to win in Michigan. That'll be also a bad idea. So it really tells us that yes, correlation versus causation really important, especially if you want to act on the world. We have to really think causally. So, but then the question is that I never thought about the causality too much until about 2018 or 2019, and only around, say, 2020, I started to think a lot about the causality. I should have thought about it much earlier on, but I started to think about it only about 2020 because I think now is the right time to think about this one, the prediction versus action. And then the reason is there's been a lot of progress in prediction or building a very, very strong predictive model so that now we can actually move beyond this kind of correlation-based prediction and then trying to think of how the predictive models or the strong prediction that we can make can help us think about the causality. And in fact, really the correlations, I actually don't even think that we need to think about it that much. All those large-scale models that you use every day these days, those large models coming out of the OpenAI, large models coming out of the Anthropic, Google, and whatnot, these models really capture all possible correlations you can imagine in the large amount of the data set that is completely unimaginable now. And then that's exactly what we did over the past, let's say, half a century in machine learning. That's trying to ensure that the vanishing gradient is not an issue by, let's say, introducing residual connections, attention mechanism and whatnot. That's trying to make sure that we know how to minimize a highly complex, let's say, loss function in this, like a billion-dimensional space by using stochastic gradient descent with the adaptive learning rate. So we've done all those things. So if you look at the loss curve of any of the large models that are being trained, now one of the examples that you can check out is the Open Athena's Marine project. They actually even release the weight and bias artifacts as well as the logs as well. So you can see how the 200 billion parameter model's training loss actually changes. You can track it at every step. And then what you see is that the perplexity, or you can think of it as a cross entropy, it goes really, really low, and then it goes down further and further to the point that I almost feel like we are actually getting to the true entropy of the data. We're really capturing every possible correlation that exists in the data set. And then this really allows us to now go beyond and then think about the causation so that we can now use these predictive models to act on the world. So this was my motivation. But then, of course, after reading about all those textbooks, trying to think about what causal inference, causal discovery, and the causation itself is, I realized that we need to first have a quick discussion about what a cause is, because I got really confused at some point. What is? And then whenever I think about the causal mechanism or the causality or the causation not necessarily equating correlation, there is always this discussion about the physical mechanism, or somebody will always bring it up. As in, will the causality or learning about the causality tell us about the physical mechanism behind which all those observations that we make arise? I realized that that's actually that's probably a wrong way to think about it. That's just a wrong level of the abstraction. So let's just define the cause in one particular way. And then by describing this, we're going to see that there are many different ways to define cause. So one way to define, let's say, marginal cause of any of the outcome y, so there should be outcome not effect, can be thought of as is the distribution over y, the marginal distribution over y change had I intervened on one of the potential variable that I could have intervened on, and then that's going to be the effect. If they are different, x actually impacts the distribution over y, so there is the outcome, so thereby it's probably a cause. Kind of makes sense, reasonably so. And in particular, if I have only two variables, x and y, this is exactly how we think of the cause. But of course, if you have a lot of the other variables, then marginal cause may not be actually not the right way to think about. Maybe we should think about the combinations with the other variables. Maybe we should look at all possible combinations. But then it becomes a bit less interesting as well as the computationally very intractable. And this really tells us that in fact, the way to go into the causality is to think about what is even a cause. What is the level of the abstraction at which we need to operate? And one of the, let's say, major kind of example I started to use in order for me to think about it and for my students to think about it is this cigarette sales and the lung cancer death in the United States. This graphics is actually really great. So the blue curve that you see here is the sales of the cigarettes in US over time. So at the end of the 19th century, in fact, the number of the cigarettes or the, let's say, manufactured cigarettes that are being sold, it's like negligible. You cannot even see you don't even have a statistics. However, it's starting to go up, starting from the beginning of the 20th century.
Is it normalized by the population size?
This one is not normalized. The sales is per adult. So yes, it is normalized by the adult. So this is in fact the number of essentially the cigarettes that are being sold per adult. That's true. And then what you see is that you see these, famous or the popular, let's say, cigarette brands, Camel, Lucky Strike, Marlboro. And then this is about time people realize that, we can actually have amazing marketing campaign in order to boost the sales. It goes up and up and up and up. And then the red curve is the US death due to respiratory cancer per 100,000 people. And then what you see is that this time from the 50s, that curve also started to go up. And then in 1963, the US Surgeon General, in fact, now finally makes a recommendation or the announcement that smoking seems to cause cancer, and in particular the respiratory cancer. And then the US started to put all those regulations on the cigarette, let's say, marketing as well as the sales. That's when you started to see all those disgusting, let's say, pictures of the lung of the cancer patients and so on the cigarette packs. And then the TV ads were banned as well. And then this gap is uncanny. There's about 20 years of the gap. And then from there on, the death rate due to the respiratory cancer also started to drop. And then this is a kind of one, let's say, amazing representative example of the causality actually having impact on the society, in particular on a very positive way. So that if you look at the death rate due to respiratory cancer, it come down all the way to the level of the early 20th century by now. And then this is really interesting because somehow in this whole thing, we just thought about the two variables. Are you a smoker or not? And then are you going to have a lung cancer or not? Or it can be any kind of, let's say, respiratory cancer. But this is clearly not how the world works. It's too simple, right? And then the nice thing is that I worked at a big pharma for 4.5 years. So that gives me a lot of thought about already view about how we should think about the disease and then how we think about the treatments of the disease. And I can absolutely tell you that between cigarette smoking and the actual lung cancer, there must be about tens of the millions of the steps in between. Because cancer is how your cells actually have a mutation and then thereby start becoming immortal, let's say, cells that have a negative effect on your body. and smoking is the behavioral, let's say, behavior that you take. So many things need to happen in between, but then we just somehow decided that this is the right level of the abstraction. Why? Because smoking is the one thing that we know how to intervene at a public policy level for everyone in the society. In fact, if you wanted to think about the actual mechanism by which the cigarette smoking causes cancer down the road, we should look at this nice handbook that was published in 2010 by the CDC. And it really is a kind of very extensive, let's say, book that accumulates all those set of evidence as well as the papers that have been written down about the pathway between the initiation of the cigarette smoking all the way to cancer. And then each and every box here has about another, let's say, 10 to 100 boxes within it as well. So that's the kind of, let's say, rough level of the mechanism that we know. But we decided to kind of, let's say, avoid or ignore all those intermediate boxes and then said that the word actually works in the way where there are two variables. And then the treatment is going to be smoking, and then the outcome is going to be whether you get lung cancer or not. So I'm trying to emphasize that the causality and mechanism should be separated from each other. And then what I'm going to talk about in the rest of the talk is going to be purely on the causality. Once we make some decision on the level of the abstraction that we want to operate, and then we're going to perform the causal inference, discovery and whatnot in that kind of, let's say, level of the abstraction, not at the actual physical mechanism level. Because even this has nothing to do with the actual physical mechanism, right? I'm gonna say, okay, loss of normal growth control mechanisms. You can imagine that there must be like the millions, if not billions of the steps that we need to think of if you want to think about the actual physical mechanism there. And in fact, this is one of the most successful ways to think about the causality, in particular if you think about the medicine and healthcare. Let's think about the aspirin. I'm pretty sure quite a lot, most of you probably have taken aspirin at one point or another in your lifetime. And it's one of the most effective and the safest drugs that you can ever imagine. And it's from 1899. Bayer actually named it aspirin, and then they started selling it back. So it's like it's like a 120-year-old drug that has been used. But only in 1971, the British pharmacologist figured out that here is a one way by which aspirin actually works to suppress the headache or whatever the pain that we have. And then received a Nobel Prize in Physiology or Medicine in 1982. So it took about 80 or so years. But then the funny thing is that if you just go to Wikipedia, of course, that's the source of the truth. Wikipedia and then go to the aspirin page, what you notice is that we actually still don't know fully how aspirin works. We take it, the whole humanity has been taking it nonstop over the past 120 or so years. And then we thought we figured out how it works, and then we even gave the Nobel Prize to the British pharmacologist in the 1980s, but we still don't know how aspirin works fully. We have some theories. We believe that it's probably due to the decreased production of the prostaglandins and TXA2. Maybe not. But that's fine, right? So this is actually one of the examples where we don't know the mechanism, but we know the causation. That is that if we give aspirin or if we take aspirin, then it's going to result in the outcome that is at the reduced level of the headache that we're suffering from or some kind of pain. Now, of course, I do have a counter example or the bad example of ignoring the mechanism. And then it turned out that that's actually the same by the same company, Bayer. Bayer is an amazing company. They invented aspirin, but also there's something called the heroin. You probably heard of. And then you wonder, why is it called heroin? That's a too good a name to give to this extremely addictive substance. So Bayer actually invented heroin as a non-addictive alternative to morphine. And then they named it heroin because Bayer is a German company as a heroin, right? And then started to sell it as the alternative to morphine. In fact, that was actually sold as a treatment for the morphine addiction as well. Until the point they realized that, actually, this is way more addictive than morphine itself. They stopped it. But again, we still don't know exactly why heroin was considered less addictive than morphine, or why it is actually more addictive to morphine. We still don't know yet exactly. But somehow we know because we were able to perform the causal inference using experiments directly ourselves. So it's going to be about the causality, not the mechanism for now. So then how do we infer a causal effect? I'm going to talk about some of the kind of, let's say, very simple traditional way to do so now. But before I continue, if there is any questions or the comments, I'm happy to hear about them. Yes, Shai.
I was turned up by causality. So first of all, this thing that the equation that you gave, if there are many factors affecting, it could be that eliminating each one of them will not affect the outcome, but they're still together the cause for the outcome.
Yes.
And the other question I have is about sometimes we know the mechanism, but we can never, I mean, I know that if I jump from a plane with a parachute, I don't die because of the parachute. I know the mechanism, but I never conducted an experiment in which I threw two people from the plane, one with a parachute, one without, and see what the different outcome.
That's true. Yes, I'm going to actually talk about the second question when I talk about the causal inference side. But you're absolutely correct. The reason why I added the marginal there is because in the original version of my slide, I didn't say marginal. And then there were a lot of questions about it. But what if we actually have other variables that in this particular case are marginalized out implicitly, but in fact have the effect, right, when conditioned on that one? You're absolutely correct. And then that's the reason why I put the A marginal cause here. And then it's actually one way to define what a cause is. And it turned out that the precisely saying what is the cause itself is a ill-posed problem unless we start putting a lot of context and assumptions. So yes, you're absolutely correct. This is one example of that, yes. And I'm going to actually get another example shortly afterward. Yes.
Can you clarify again, like how we can distinguish correlation versus causality if we don't actually care about mechanisms? Because they'll say like people live longer if you eat meat, but then maybe that's because people who can eat meat can live longer. So
yes, absolutely. So we're talking about the potentially unobserved confounder, and then that's kind of a weird thing. Is that I'll talk about it at the very end. Is that when it comes to inference, could be causal or just a usual statistical, even the logical inference. It a lot of times, or at least traditionally, it has all boiled down to what kind of assumptions we're going to set. So in causal inference, in a traditional, let's say, sense, one of the major assumptions is the ignorability. And then that's going to correspond often to the non-existence of the unobserved confounding. So yes, only then we can talk about this one. Now here I actually made everything a bit simpler, but the original debate about whether cigarette smoking is bad for your health or not had one more variable. And then there was a genetic factor that affects smoking and lung cancer as well. What if there was a particular mutation that made people be more prone to, let's say, addiction by the nicotine and also causes a lung cancer? And then interestingly, a lot of the famous statisticians back then, such as Fisher, were on the side that in fact that factor does exist, thereby. And then he was a famously heavy smoker while smoking, saying that that's just a mutation, and I probably don't have a mutation kind of argument was making. You're absolutely correct. So here we actually, as a whole society, when the Surgeon General made an announcement, we decided to make that assumption that that confounding is probably very, very weak or non-existent. However, once we assume that the confounding exists or we found a particular confounding factor, then the conclusion will, in fact, flip. You're absolutely correct. Yes.
I'm thinking about, do you have time also into the factor, because the direction of cause and impact might be reverse also, but there should be a time component, temporal component.
Yeah, absolutely. That's a really interesting thing. So let me go all the way here. So the time definitely should be considered, but how do we actually take the time into account is a kind of an interesting question here. So one way you can imagine is that if everything is observed simultaneously always, and then without any kind of delay, then of course, time will tell us that, okay, one particular aspect, that is that the cause cannot happen in the future, right? Cause cannot happen in the future. Cause can only happen in the past, right?
If you drive in Israel, the car starts driving through the intersection before it turns green.
Yes.
They know it's going to turn green.
Right, that's what I meant is that if everything is simultaneously happening, so there's no delay or the prediction. So the prediction can be thought of as a reverse delay. So if there's a delay or prediction, then the time alone is not enough. So with the particular set of the assumptions, yes, Granger causality is one way for us to think about it. Yes, cause must precede the effect outcome, thereby we can actually establish it. But we almost always have a different delays in observation across the different variables, to the point that using just a time as a signal is very difficult. Yeah, it's a very narrow subset of the cases that we can use a time.
Yeah, while on the go to the causality versus mechanism.
Yes.
Yeah, like, okay, the thing is, you say that smoking causes lung cancer, the higher level of drug than this, but it would seem to me that each one of these up is a causality itself. I mean, receptor binding does cause protein kinase A and B activation and other things.
Absolutely.
So why are you using squares here instead of circles? It seems to me that this is just a lower level.
You're absolutely correct. So this is a higher level abstraction of what happens. However, we often don't know the correspondence. So where does a cigarette smoking start, and then where does a lung cancer start? It's somewhere in between these two extremes. We often don't know, and then sometimes we're going to in fact ignore some of the parts that exist here as well, because there could be definitely other factors that affects lung cancer a lot, but we might actually just ignore them. Just like that genetic mutation that I just talked about earlier. All right, so more in a traditional sense, I saw that there are actually quite a few statisticians here, so I'll be very quick, and then I did not go into details because I'm probably going to get the details incorrect. But what is a usual way to represent this kind of, let's say, how we set up the problem is that we're going to define some kind of universe, right? Because the whole universe, once we start thinking about the whole universe, everything is confounded by the Big Bang I heard, so it becomes really difficult. So we're going to make some restricted box under which we're going to perform causal inference or discovery. And then within this box, we're going to have some finite number of the variables. And then those variables correspond to some events. And then we're going to say that there are edges that connects these variables so that we know that there exists some true, let's say, causal dependencies among these variables. And I'm going to actually assume that this acyclic graph, that I'm going to ignore time. I'm going to say that we're working on a time invariant setup. And then for each of the edges we have, or each of the variable we have a conditional distribution over that variable, given all the other variables that are the parent nodes of the variable. And then causal effect inference answers the question how, why the outcome responds to our intervention on a action or the treatment under some conditions. And then there are many different effects that we can measure given this setup. So one of the most popular, one of the most widely used one is the average treatment effect. On average, what is the difference between the outcome when I acted on the treatment by providing the treatment versus a placebo? Or another one is a conditional AT. Conditional AT is actually much more important in the sense that we don't want to look at the entire population because it's possible that there is a subpopulation over which the treatment is actually effective while the other people won't actually have the benefit from that. And then one of the examples, and then the conditional average treatment effect is the D quantity that we use in order to find medicine or the drugs. And then this is, I'm going to give you one example called the Herceptin. Herceptin is an antibody therapeutics for the breast cancer, but it doesn't work for all types of the breast cancer, but it only works for the one particular type of the breast cancer. So that is that the patients who have the breast cancer and have the overexpressed HER2 gene or the HER2 proteins. This one doesn't work at all. Doesn't work for the other patients who don't have the overexpressed HER2 gene expression. But then when Herceptin is given to the patient with the overexpressed HER2, it's actually magical. It effectively prevents the patients from death. Before, most of the patients with overexpressed HER2 before Herceptin, in fact, it was effectively fatal. And then this really tells us about how this kind of effect is measured, and then depending on what kind of effect we measure, we can actually draw different conclusions and then also come up with the different, let's say, benefits. But at the end of the day, most of the effects can be computed based on this particular quantity. That is, what is the expected outcome given my intervention on A, let's say treatments, and then some, let's say, covariates that I'm going to condition on. I'm not going to talk about the individualized, let's say, treatment effect, because I have this kind of philosophical, let's say, conundrum that I'm suffering from at the moment about, does individuals exist? It's a question that I got into recently. But anyway, so if we know how to compute that one, it really allows us to really compute any kind of, let's say, effect. So let's think about how we can actually compute that effect. Now, that doesn't mean that computing that expectation is the best way to compute various types of effects. Some effects we can compute directly without computing this expectation, but we can often write it down as computing this expectation and then deriving the other types of the effect. So what is one of the most typical way is the inverse probability weighting. We want to avoid this kind of confounding if I observe all these variables by making it so that the distribution over A given X is uniform, or the unconditional. That is that the distribution over A is going to be same as the distribution over A given X. So relatively straightforward, you can derive this very easily. This is one of the most widely used technique for doing an observational causal inference. And then the other way that is most probably considered as a gold standard is a randomized controlled trial. I have a subjects who participate in the study. I'm going to randomize their assignment to either the treatment group who are going to receive the actual treatments, or the control group where they're going to receive the placebo, essentially sugar water instead, and then trying to see how the outcome looks like. And then if the outcome for the treatment group is significantly better than the outcome for the control group, we declare a success. Now, there are a lot of, let's say, controversy about whether RCT is the right thing to do, and the only thing we need to rely on, but at the moment is considered the gold standard. And you can imagine that it's really, really difficult. Why is that? Is that we have to run experiments, and running experiments is never easy. Most of us are computer scientists. We got lucky because we somehow, as a whole community, over the past century, set up the computational system so well and standardized it so well to the point that we can run all those experiments on the fly and then see what kind of things happen at the software level. However, when we work with the real world, in particular, if you work with the patients or the humans, setting up the experiments, ensuring that we're not going to harm anyone who is participating in the study is really difficult. And not to mention that it can take a long time. Let's imagine that you're going to come up with an Alzheimer's drug, and then you want to test it, and it turned out that you need to give this Alzheimer's drug to the patients who are in their 20s and 30s very early on. How do you know that this Alzheimer's drug was actually effective? You'll probably have to wait about 25 years because the actual symptoms of the Alzheimer's will often show up very late on, let's say in your late 50s, late 60s, late 70s. But maybe your drug only works if it was given during late 20s. Then you gotta wait 30 years. Otherwise, you won't be able to tell whether your drug was effective or not. So you can see that it's very, very difficult. That's the reason why we want to actually use the already collected data using clever algorithmic techniques. Unfortunately, that turned out to be even more difficult because we have to be very, very careful about whether it is even possible to begin with. Can we really identify the correct causal effect based on the already collected data? And then it depends on how the data was collected, what kind of problem we're solving and so on. So it turned out that that's very, very difficult problem in general. And then I'm pretty sure no one actually can argue that it's difficult. There's a reason why we only get, let's say, about 5 approved drugs every year, because it's really difficult problem to solve. And then in doing so, we have 3 problems. First one is that we need to be able to find causes that we want to intervene on in order to maximize the outcome. And then second is that given that we have discovered these causes, we need to be able to estimate the actual causal effect of a particular cause on the outcome. And then third one is the causal identification. That is to answer whether the causal effect can be identified. Now, if you're a statistics student, or if you took the, let's say, statistics course, then usually we teach this in the opposite direction. We're going to often teach about the causal identification or the statistical identification first. And then when we say that, oh, yes, if things are identifiable, then let's think about the estimation algorithm. And then often discovery kind of as it comes on the side. But this time I'm going to go in this order because in my opinion, this is a right way for computer scientists to approach the problem of the inference. But you'll see what I meant by the end of my talk. But then at the end of the day, the first two problems, and the third problem I'm going to get to it a bit later, first two problems can be cast as finding an algorithm F, right? Cool, what is a causal discovery? I have a bunch of samples, X, and then I have a set of variables. And then the goal is to have this function that's going to give me another set of or subset of the variables that may be the cause of the target variable. So here's a bunch of samples, and then here's a target outcome that I'm interested in it. Now get me enumerate all those variables that may be a cause of this particular outcome. So it's really just the set to kind of set a function that we need. And the causal inference is very similar. It's even simpler. We start with a bunch of set of samples, and then we just want a single scalar that is the causal effect that I'm interested in. And then this is set to scalar prediction. So it turned out that the first two problems, called discovery and the causal inference, are really nothing but just finding an algorithm problem. And then in fact, until recently, this is what a lot of people in causality or the causal inference have been doing. For each and every problem, we're going to manually write down this algorithm and then say that they show that how this algorithm works well under a set of assumptions that they're going to come up with. And I'm going to call that an artisanal way of designing algorithms. But now, we're now in an industrial revolution. We're just going through the industrial revolution in algorithm design. We're not going to do the artisanal algorithm design, sitting down and then trying to come up with some algorithms. We're instead going to rely on amazing machinery called large-scale machine learning to find algorithms automatically and systematically. So yes, we talked about the Lambo earlier. Yes, that's a great car. It's very, very low volume production. Because a lot of things are done by this kind of masterful, let's say, car designers and manufacturers who are making it. But now we're going into the era of the Ford. Yes, each and every car may be worse than Lamborghini, like Ford Focus. Of course, if I had a choice, I'm going to buy the Lamborghini if I could afford it, right over the Ford Focus. But now, because of the Ford Focus, everyone can drive. I think that's where we're going to. But what changed? What changed is that these large-scale language models showed us the way that is that in context learning is that we can actually use these large-scale language models in many different ways by showing them examples as well as the descriptions of the problems. So effectively, these large models that we have are not really there to solve one problem, but they are actually learning how to solve a new problem down the road. And if you can actually test it yourself. Whatever the language model you have, you just open it up, give the description of the problems, give some examples, it's going to actually solve it very, very well. And it's not only for fuchsia learning. So when this kind of in-context learning or the meta learning was proposed early on, over and over, almost like every decade there is a meta learning, the in-context learning or whatnot. But then it's been always a fuchsia learning, like 5 examples a class. Very uninteresting. Who cares about the 5 examples? If you have 5 examples, do the nearest neighbor search. And then try out all possible distance function that you can imagine. That's the best thing you can do. But now, we're in an era where the compute is abundant. Of course, relatively, compute is abundant. And then these models have been trained on an amazing amount of data to the point that in the context, you can give like 2,000 examples, the whole data set, and then ask the model to answer for the new instance on top of that. And then many of these more recent models work with the context length of the million, if not 10 million tokens. With the 10 million tokens, in fact, you can actually add in an entire code repository, the entire data set you're working with, and so many other things that you can do. we're really in an era where now we can ask these language models to learn the algorithm itself that takes as input a full description, full data set, and then give me just a single number that we really care about. So what I'm going to tell you is that yes, we can do it. We use exactly same mechanism or the tools that we have built over the past, let's say, half a century to get to this kind of large-scale models, and then we're going to use that for the causal inference. So let's look at the learning to discover, learning to estimate, and then learning to identify at the very end as well. So what are these problems? It turned out that they're all connected with each other. So we start with some causal model, sometimes known, sometimes unknown. And then this kind of structure comes together with the actual functionals or the mechanisms. So those are conditional probabilities using a sampler. The sampler could be actual experiments, word, or some synthetic, let's say, sampler. We get a bunch of samples. So a bunch of samples often comes together with the covariate, whether some of the variables were intervened or not, and then the actual outcome associated with it. And then given this set of samples, if we estimate the causal effect, so given the set of samples in the causal model, that's what we call causal inference. And the causal discovery is given this set of samples, can we actually figure out something about this underlying structure within this our restricted universe. And then the learning to identify or causal identification could be, well, can we actually solve this problem of the causal inference? But I'll get to that one later because that one is kind of, let's say, both interesting, but also at the same time trivial in my opinion. So I'll tell you about the 3 ongoing studies. Well, one of them is completed, so targeted cause discovery, and the second one is a black box causal inference. This paper is kind of, let's say, it's very challenging paper to publish, but the preprint is online. And then the last one is the one that we just submitted to Neuro, so do let me know. We're about to actually post a preprint on arXiv, but it might take a few more days to kind of, let's say, get all the details correct. So learning to discover first. So targeted cause discovery is where we try to figure out what are the potential, how to enumerate all possible causes, either they are direct or indirect. Most of the recent work on the causal discovery sadly either does, let's find all the direct causes, or let's figure out the entire structure, that is the dependency structure of all the variables. But as we learned earlier, or as we talked about it based on the smoking causes lung cancer, often what we want is that we want to enumerate all possible causes and then decide which cause we're going to intervene based on our ability to intervene. Some of those the biological mechanisms that we saw on the slide earlier are not interventional. We cannot really intervene on them. We don't know how to do that. Smoking, we knew how to do that, so that's why it actually made sense. So here as well, so the goal here is that we're going to just enumerate. And it's very simple. This one size says it all. We're going to prepare a meta distribution, so some kind of prior over the potential causal models that includes a structural causal model as well as the conditional distributions associated with all those variables. We sample a causal model S, draw a lot of samples from D, and then by drawing a lot of samples, we can actually estimate whatever the effect because we have the ground truth. And then we're going to update this discovery algorithm F that is just nothing but a transformer to take as input this set of samples and then output a list of all those variables that could be the potential cause of the target outcome. And then we use a stochastic gradient descent, and then we do it over and over until the point at which loss actually converges. Yes?
How is it different from inductive machine learning?
It's essentially exactly the same thing, actually. Yeah. Yeah. So, now of course, if we wanted to do it in 80s, it would have been a bit difficult because we didn't have enough compute, and we didn't know how to train these large-scale models well enough. Because all those tricks that we have actually come up with over the past, let's say, 15 years really allow us to train these kind of large-scale models. And then in particular for the parameterization of this f, the function, we're going to use this kind of, let's say, network architecture that was proposed by the local 2022. We do the attention over the 2 axes. That is across the samples and then within the samples. So they actually work with the variable number of samples, and then it is permutation invariant there, and then it's permutation equivariant, but can also work with the variable number of the dimensions as well. And then we just stack them up on top of each other. And then at the end, we have the multi-layer perceptron that's going to actually tell us which of the variables is a potential cause there. And we can actually scale it up to high dimensional observations readily so if we use a bit of a mathematics and the statistics here, but I'm going to skip this detail for now. And I'm going to simply tell you that this is how we train. So the whole thing goes in as the input, and then we do some subsampling because we only need to work with, let's say, hundreds of thousands of the variables. And then this is going to generate these partial code scores. And then we try to just minimize this code score against the actual, let's say, known causes. That's a binary vector. And then once training is done, we do this kind of, let's say, ensemble averaging in order to get the estimated code score. Now, when we do this, how do we know that this actually does something interesting? Then the easiest way is for us to think about how I would solve this problem if I knew how to do it. And then the simplest way I can imagine is that, well, it seems like some people have come up with a way to predict the entire graph structure. And then if I know the outcome, I'm going to just do the graph traversal to just enumerate all the parent nodes. That sounds reasonable. But what is the issue with this algorithm? This naive algorithm is that the error rate is going to go up as I go further and further away from the target outcome variable. Because if I miss one of the edges, I'm going to lose everything on beyond. So then the question is, will the model trained in this way also exhibit that kind of, let's say, footprint, algorithmic footprint? If it doesn't have the algorithmic footprint, then we know that this model is solving the problem in a slightly less trivial way, perhaps doing some kind of pairwise independence testing. But we all know that for the pairwise independence testing to work, we need a lot of samples. And even then, sometimes it's not going to work well. So we tested using a simulator on the gene regulatory network inference, because this is a detail, but you can trust me that it's a reasonable simulator that is not perfect. But we can actually generate a lot of, let's say, simulated examples. And then using that one, we generated graphs with the 1,000 variables only. And then we just use a random graph, like the actual random graph, scale-free random graphs, stochastic Blanc models with 1,000 variables. And then using that graph, we ran it through this simulator called the Sergio, and then generated these observations. And then we tested on a real gene regulatory networks that has more genes than just 1,000 variables. One of them, E. coli, 1,500 genes, and on yeast, let's say more than 4,000 genes. And then we want to see if it works there. And at least for the E. coli, we know exactly what the gene regulatory network should be in general, so we can actually compare it directly. And then what we see is that unsurprisingly, it works. This TCD DLS ours works much better. It's like the recovery rate essentially compared to most of the other algorithms. And in fact, what we see is that in this problem, purely correlation-based approach completely fails. It gets slightly better than random chance. And then these are the other algorithms that actually does a full, let's say, causal discovery of the whole causal graph, but they also fail because as they recover this full graph, they of course make some mistake at some of the edges. And then once they make a mistake on one edge, everything beyond are all lost. So we looked at that one. So x-axis is a cause-effect distance, so distance between the outcome and the potential cause. And then we look at the false negative rate, or you can think of it as an error rate there. So the Gini3 and Avicii recovers the full graph and then does a graph traversal. As the distance increases, error rate goes up. But what we did, that is that let's just predict it directly. This algorithm, the error rate is pretty much constant with respect to the distance. This tells us that it is solving some kind of independence testing like problem, pairwise one. And it doesn't really reconstruct a full graph behind this whole problem, which actually tells us that, yes, this approach did find an algorithm that is better than kind of, say, my dumb approach that is that, okay, let's get the full graph and then let's do the graph traversal. And then this actually generalizes computationally, at least computationally, to, let's say, the actual human data set as well, which has about 20,000 genes as well. So we can train a model on the 1,000, let's say, nodes, it generalizes to 20,000. Now, obviously, we don't have the ground truth in the case of the human gene regulatory networks, but we can actually check very carefully and then painfully, one at a time, whether it was actually mentioned in literatures or whether those are actually known already. And this, it does recover quite a lot of the known things and it does find some things that we didn't know before. But of course, whether this is correct or not, we will need the actual experimentation down the road. So this was a discovery part. This really tells us, this was one of the indications where it told us that yes, if we have just a rough simulator, not even the perfect simulator, if we can generate a lot of examples, we can train this kind of large scale models to solve the problems that are more like the algorithm-like problems rather than just simple pattern matching and classification there. So we decided that, well, we gotta continue on. If we can discover some of these causes, can we also do the estimation? Estimation is relatively straightforward. What we're going to do is same thing. We define some meta distribution of the prior. Well, if there's a question, maybe I can.
Sorry, on the previous part, can you speak to the order of magnitude of the number of samples you need?
Oh, yes.
1,000 variables.
Yeah.
It's super exponentially the number of possible graphs that you can have on 1,000
Absolutely, absolutely. So if I think about testing every possible graph, it's impossible. It doesn't work actually. It shouldn't work. Now, one is that that's the reason, and then you have the fact, and even then the fact that it actually does actually get a very high, let's say, accuracy. It tells us that it's not actually doing a graph, let's say, structure recovery here. It's really finding a causes or the potential causes, indirect causes as well. And then my suspicion is that it's doing a pairwise independence testing, something along that line. But that is amortized, and then there is specific to these families or the graphs, these families of the graphs. So can it do it with the 0 samples? No. But yeah, the nice thing is with the synthetic data, we just generate the data over and over. But then everything was run in a very reasonable amount of the time. I forgot exactly how many iterations we run. In the paper, we actually discuss about that as well. But the convergence is pretty stable.
And how do you determine what ratio of observational to interventional data?
Yes. That's actually, so we actually do have to simulate the random knockoff, so the intervention as well. And then in this particular case, we actually did choose a one particular, let's say, number as the interventional data ratio, and then just did a true, like, a random knockoff. Okay, so estimation, relatively straightforward. We define the prior over the structural causal models, sample from it, and then given that structural causal model, we're going to sample a bunch of, let's say, points while intervening on some of these, let's say, variables. And then we use a Monte Carlo to produce the ground truth causal effect. So if there is a bit of a noise, and then we simply train a set transform or plus to take us into this set of samples and then predict this causal effect. Just a regression problem. We just train this one. And we can write down something like the Mackey-like thing, the composition of the bias and variance. But of course, in this particular case, we get actually a few more terms that are interesting. And of course, there's a Monte Carlo error. And then that error, we can reduce it by just sample more and more during the training time. There is a finite sample error. We can actually give a larger and larger data set to this model, and then it's going to shrink. There's estimator variance as well, because we're only using a finite set of data sets. But one thing that I want to point out is the identification error. We're going to get to that one. That one we cannot actually reduce ourselves. There is an issue. Yes.
Are the errors the counterexamples?
Sorry?
The counterexamples are triggered as errors.
Counter examples.
Like in the model, you inductively generate the model from the examples, right? So if there is one or two counterexample exist in the sample, how do you deal with that? I think that's
going to be the identification error, essentially, right? Yes. So yes, if things are not identifiable, thereby the identification error is large. However, the training loss actually doesn't go down below that one. So we can actually, the diagnosis is actually for free. I'll talk about it in the causal identification shortly. So we call it black box causal inference. And then we just tested on a bunch of setups for both known, let's say, good estimators and then unknown good estimators. So and then it's a very low dimensional case. When we have a confounder, will it work well, against the MLP or the linear regression? If we have an instrument variable, will it work better than the two-stage linear least squares? Or if we have a proxy, then can we use a proxy plus the two-stage linear least square estimator? And then what we see is that the BBCI just kind of works almost always. It just works because it's how it's trained to do. So unlike many of these estimators where we thought a lot about the setup and then wrote down the estimator, BBCI, in fact, tries to minimize this error. So when we train this neural network, we're explicitly minimizing the variance as well as the bias. And then the remaining parts are the ones that anyway cannot be minimized directly. So this really defines the estimator that really we want. We're doing a search in the space of the estimator that has the desirable properties, low bias and then low variance. And then we really do see that. And then what is really interesting is that I'm going to skip this one, is that there's some of the setups where we don't really necessarily have a standard approach in terms of the causal estimation. BBCI can be just used as long as we can just simulate a similar but not same cases over and over. So when we have the mix of the interventional and observational data, what is the right estimator? Every problem that you're going to run into will have a different estimator, but in this particular case, we just train this black box causal inference algorithm, and then it simply just works. And while some other estimators sometimes completely fails as well. And then we can, one issue with the causal inference is that we often don't really have the ground truth. But there are some data sets where we do have the ground truth. This is one of these examples that was released by the Lalonde. And then it is based on the national supported work, NSW demonstration, or the program implemented in 1975, because they actually ran the randomized controlled trial with this program. And then we do have a lot of the observation data from the other parts of the country where they did not implement it immediately. So we can actually compare the outcome. And then what we see is that the black box causal inference that uses some of the actual observations from that, as well as the distribution we know, is always going to recover the correct, let's say, effect more precisely and with a lower variance than the other estimators. And this was a really nice kind of, let's say, example of how it worked. Now, when we are running these experiments, we made one mistake. Once we made a mistake and then we forgot to add in some of the covariates that are known to be very important. But we kind of just made a mistake in the coding. And then we started training this black box causal inference model. And then what we noticed was that the training loss was flat. We're just training over and over, and then we kind of debugged everything about how we implemented stochastic gradient this, and debugged everything about the set transform plus, and on. It was just flat. And then we found out that we forgot to add all the covariates. We added one covariate at a time to make sure that everything was included, and we saw that the loss would drop just a little, and then flat. And then at some point, when we added all the relevant covariates, it just dropped to the zero, almost instantly. And then that actually told us that what if this kind of bands that we saw corresponded to how identifiable, like it's a weird thing, not whether, but how identifiable this particular causal effect is under a particular context. There is availability of the covariates. So this is the final thing that I'm going to talk about. We're going to just focus on this one, identification error. So if you try to minimize the actual loss, that is that whatever is predicted by the neural net against whatever the true, let's say, causal effect is, it's going to minimize the third and fourth terms. We can minimize the first term by just increasing the number of the Monte Carlo samples we use, but the second term cannot actually go down. It's just actually fixed. That's the best we can do because of the identification mismatch. And then when we think about the identification, the top one is what we often think about, mathematical identification. We're going to think about the conditions really carefully, and then we're going to talk about the target space, and on expectation, is it identifiable under a particular set of the assumptions? Say that those assumptions often change across the different problems. But then what we can now think about is that let's flip it all around, because we are searching for the estimation algorithm using an optimization. Perhaps we can now define a computational identifiability. That is, under the computational budget that can be described in terms of the actual, let's say, computational constraint, or the prior over the hypothesis space as well as a problem space, the problem is identifiable if we can solve this problem within certain error threshold, let's say epsilon, for more with the probability 1 minus delta. So we're going to turn it into the computational version. So we're saying that we care about the identifiability of the causal quantity if computationally we know that we have a high chance to solve this problem. And then this is just flipping the black box causal inference, right? Black box causal inference was well, here's a space, here's a prior over the problems. I want to find the solution that's going to actually solve this problem. And then if I can say that if I can almost always find the solution over large number of the problems with the low, let's say, error tolerance, then I say that, okay, this was actually identifiable problem. Yes.
Do it with respect to a given algorithm, or you just quantify over the existing algorithm, which we never know?
Right, that's true, yeah. So in fact, you kind of say skip this slide, but this is a traditional one we'll skip. This traditional actually doesn't talk about the estimation algorithm at all. Identification is not tied to the estimation, but now we're able to say that if there exists an estimation algorithm that has the expected success rate of estimation within a given hypothesis set under a threshold epsilon, that is at least 1 minus delta, given a prior distribution over prior distribution over SCMs, okay, not prior over the prior over the SCMs, then we say that the causal quantity is identifiable. Literally, we're going to say that if the loss is low, that's great, because the estimation algorithm exists for most of the problems in this, let's say, space of the problems. So it's a kind of, let's say, different way to think about it. So how to tie up the estimation algorithm and identification, but instead of thinking about the identification and then trying to think about the estimation, we say that, well, we know that there is an estimation algorithm because we found it using an optimization problem for a lot of these kind of problems that are like reasonable under the problem space, thereby this is identifiable. And then anything else, we actually say that, well, we couldn't find the solution. What does it mean for it to be identifiable? That's kind of, let's say, the flipping of the, let's say, philosophy here. And then in fact, the nice thing is that once we do this, after training is done, on a new set of data points, from a new problem, we can now compute the posterior over the identifiability. Now, identifiability is a random variable. We can estimate the posterior this probability, and then based on the error tolerance, we can draw these curves, and the more identifiable, we're going to get a larger, let's say, area under the curve. And it's very smooth. This actually tells us that within the computational budget, which problems can we solve, and which problems are more difficult or easier to solve. So we tested all those things. I'll share the preprints. Just email me, but we're going to upload it somewhere. But one example is a mixed observational and interventional data with a distribution mismatch. What if we have an interventional data, but the interventional data's intervention distribution was slightly off? Can we still benefit from this one? Then we're going to change the interventional or the confounding strength as well. And then what we see is that indeed, it actually captures precisely what we would anticipate. Is that when we have some interventional data, it's going to be the best case scenario. If you have all the interventional data, it doesn't work well because the interventional distribution is completely off. And then if the hidden confounders weight, so confounding strength is strong, then it gets worse, so going down. If confounding strength is low, then it's going to actually perform the identification almost perfectly. And it also shows that there is a non-monotonicity of the identifiability as well with respect to the sample size. Sometimes more samples can hurt, and in particular when it comes to the individualized treatment defect estimation. And then this computational identifiability actually gives us this number, like this kind of quantity, like precisely. So anyway, so I'm going to wrap up now quickly. So absolutely, causality is difficult. I mean, because there are so many problems that we need to solve. Correlation was a bit easier once we got the transformer and the gigantic GPUs. But for causality, I think that we still need a bit more work to get there. We need to solve the discovery problem, estimation problem, and the identification problem. And then they are extremely challenging, in particular for us. For us to solve any of these problems, very difficult. But maybe it's actually easier if you rely on machines to find the solutions for us. And then by letting the machines find solutions for us, we can probably solve all three problems all simultaneously, and then make it even generalized to new problems down the road. So in other words, we just make everything into supervised learning because we know how to do supervised learning pretty well these days. So we look at these three problems, and then they are ordered because that's how I believe that the computer scientists should approach this kind of problem. Come up with a procedure that finds a solution. And if the solution exists, then we know that we can solve the problem. So that is that we try to figure out what are the causes, and then we're trying to figure out what are the effects of those causes. And then if those things are actually not there. We couldn't find a solution. We say that, oh, okay, so this is computationally very difficult problem. And then I think that across these studies, we saw a big potential for causal inference with deep learning. So these are, oh, and of course, I'm not the first one to say this. There are a lot of related work. These are mostly recent works, but recent studies, if you go back, there are even more of them. But even then, I think we're just at the beginning. We need a better understanding of the causal and statistical guarantees at this meta level. Now we solve this problem at the problem level, but at the meta level, what kind of guarantees can we get? And then we need to think about the generalization because we have to define the prior over the problem space. So how well will it generalize if the prior shifts or in fact, the new problem is out of the support from the original prior that we have used? And then many of these problems, of course, the discovery we use a very high dimensional data, but most of them have been done in a very low dimensional problems. Will it actually work well systematically on a high dimensional data generating processes as well? That's another question that I think that we need to think of. Now, of course, one issue with the causal inference or the causal discovery is that it's really difficult to try it out directly in the real world, but eventually we'll have to do that one. So I think that that's the last bit that we'll probably have to do to demonstrate that it actually works really, really well. And then that concludes my talk. Thank you.
The thing is, AI hallucinates. Now, since you're using this to assist in discuss, of course, you can ignore a hallucination because you're always checking, make sure, and you're not going to publish it unless it's really wrong. Okay. The problem in my area, software engineering, okay, we're playing similar games of trying to get AI to assist in software development. The problem is that when we get a piece of software from the AI, okay, we know that statistically it's half wrong, but we have no idea what the problems are. So it's beginning to look like maybe it's worse than before, because you see human beings, when they make mistakes in software, they tend to make similar mistakes to other human beings. But AI is just all of them out. So now, so how do you get, I mean, maybe it's worse than before.
Yes. Yeah, that's actually a great point. One thing is that, of course, worse than before if you're good software engineer before, but if you're like me, who was a bad software engineer before, cannot get worse. But anyway, that's aside. So I think that the point that you're making, which is really important, is that a lot of the evaluation methodologies, metrics, and whatnot in machine learning and AI so far, unfortunately, have focused largely on making sure that the precision is really high. But as we start actually building these algorithms that are discovering something new, what we actually care about is whether the recall rate is high as well. Because if we're going to discover something, they have to be found. But then, of course, why is it difficult? Because we don't know when it's be discovered, thereby we cannot really check the recall, and then thereby we want to use the AI. For instance, this is an example. We can actually check the precision very easily, but we cannot check the recall because we don't know what are the actual regulatory interaction that exists. We don't have the full picture already. So even if our algorithm tells us, oh, there is a regulatory, interaction between, for instance, this one, LST1 gene and then TFRC, we actually don't know how to check. And then, is it hallucinated? Is it actually a correct one that has been recalled? So there is a new track called the benchmark and data sets at NeurIPS that started about, 5-6 years ago. I look at a lot of the benchmark and a lot of papers. Unfortunately, I think the whole community is still focused too much on precision, when most of this effort should actually go into how to set up the whole thing so that you can test a recall of these algorithms. And then that's going to actually help us figure out whether, in the case of the software engineering, whether there's a pattern in making a mistake by this kind of AI's assisted software engineering and so on. So yes, we're definitely not there, but I think that there is a slow change in the whole, let's say, consensus community that we're going to go into a more recall-oriented benchmark, thereby it's going to get better. I'm very optimistic.
Well, okay, I mean, in our area, we're asking people to think back of the time they spent doing it manually and doing it with AI. So are you doing similar things?
Yeah, we can do that. Yeah, we are definitely going there because in order to check the recall, right? Eventually, we'll have to actually give up on the notion that we can check the recall immediately right away. We need to keep track of what has been actually generated, what has been discovered, and over time, some of them are going to validate it to be correct, some of them are going to validate it to be incorrect. So yeah, that's what's happening.
Cool. Other questions? Okay, so what I'm going to ask is a little bit, I don't know, but is the graph, or let's say SCM, the right level of abstraction for this problem? Because I'm going to challenge the basics or the fundamentals of this problem. And I was wondering, like, imagine like we have a text that in this text we have like X causes Y. So you can create a graph based on this. Okay, but what can be like the prior between this graph? What can be seen as that?
Yeah, so I guess I'm at the more slightly at a even a higher level of the abstraction. Is this the right way to describe this universe under which we're going to perform causal inference or the causal identification? It's definitely not perfect, right? There is no notion of the feedback and whatnot, which is like random in the word, right? It doesn't really encode the dynamics correctly. Now, you can encode the dynamics here if you assume a finite length, let's say, episode, and then just unroll the whole thing. But once you do that, it's like, why did we do that? We'll just write down the differential equation instead. So there are a lot of different ways to write down this kind of a say causal model. I chose this particular one. And then, okay, so and then I believe that in fact, most of them are in fact equivalent to a certain degree, like the temporal dynamics, we can encode it here by unrolling over time and whatnot. But there is an aspect of the both the taste as well as a bit of a practice. That is, this kind of directed acyclic graph way of describing the causal model is extremely useful for computer science. For creating algorithms, this is the right way to go about. That's the reason why Julia Pearl, who is a computer scientist, an AI scientist, advocate strongly for this kind of approach. Now, on the other hand, if you're thinking about a very low dimensional, very, let's say, few variables, the cases of the very few variables, but in a very distorted manner, like in the econ, right? Behavioral economics and so on. All those variables interact with each other in a crazy way. Then perhaps following this kind of Rubin model is the right way to potential outcome framework might be the right way to go about. Or if you're working on this kind of the control theoretic work, then of course the differential equation is probably the right way to describe it. But again, in my view, they are all equivalent at the fundamental level, but each and every one of them has a different strength when it comes to whether they when we need to act. Then this one seems to be a good one for the algorithmic, let's say, action.
So, what I was wondering was, okay, now maybe we are in the scaling error. I'm not sure if that's the right way or not, but if we're in the scaling error and we want to unlock the scaling path to this, for example, causal discovery, I'm not sure whether this SCMs will be the bottleneck or not.
It is definitely going to the bottleneck. So here's one kind of, let's say, interesting question. The reason why we use all those low dimensional case for the black box causal inference is because, in fact, coming up with a random distribution over many variables and then random distribution over this conditional probability so that the high dimensional, the overall joint distribution is not going to look trivial. They all look trivial in high dimensional space. So how do we actually make it non-trivial, let's say, distribution over it? In fact, SCM still seems to be relevant. We can always generate the graphs that are non-trivial, very easy. But the distribution that is non-trivial, density that is non-trivial is very difficult. It turned out that what you can do is, I didn't talk about it, there's a work by Lucius, the first author, and me, we presented last year at the MLP, is that we can actually impose the SCM on top of an already well-trained neural network or the language model. And then essentially say that this what this language model defines, which is a highly non-trivial distribution, is a true distribution that we're going to borrow in order to simulate all those different, let's say, SCMs. Then suddenly we get very interesting distributions, and every language model encodes a different causal structure underneath it. And then we can use that to either evaluate these algorithms or even get these algorithms directly.
So thanks again for the talk. So the field of causality has some well-known impossibility results, which I noted you stayed clear of in your talk. So my question in two parts is maybe speak about how your work brushes up against that, and two, which is maybe a bit more strange. Do you think that some emergent properties that scale from the models that you're looking into can help overcome impossibility results?
Yeah, that's actually, so the impossibility, you're absolutely correct. In fact, most of the problems that are interesting in causal inference are impossible to solve theoretically, sadly. So how do we actually, so in fact, what this says, if the problem is impossible, so let's say inferring the causal effect, let's say ground truth causal effect, given the, let's say, observed data points and the causal query, if that is actually impossible, then basically this error is going to stay very high, way beyond the epsilon and stop there. Now, how do we actually avoid it? Is that the impossibility is very strict in the sense that they often assume that it's either the expectation over the uniform over the problem instances or the worst case instance. So how we actually avoid it and how I believe we should avoid it is that because the problems don't emerge in vacuum. All these causal inference problems that we solve are actually within our real world. So we have some prior information about the problems. Thereby, even if uniformly it's not possible to solve the problem, some of the problems within this problem space could be actually solvable. An example is that let's say you have a very simple, let's say, three variable case of they try to do a causal inference or discovery, and then we want to determine the direction of the arrow. If both conditions were Gaussian, and if it was a linear as well, we cannot determine it. It's impossible. However, if it's nonlinear, or they use a distribution that is asymmetric, then we can determine it often. And then what that means is that yes, in general, if you just thought about the problem with the uniform over the uniform prior, it's not possible. But if the prior was such that most of the mass was on this kind of nonlinear case, then we could solve it. That's the reason why we believe that having this kind of prior and then solve it with a computational approach may be a more actionable approach to, let's say, identification as well as estimation. Essentially, let's solve only the problems that we can solve, but yeah.
Cool. We'll maybe do one more question.
For the great talk, I want to ask a follow-up question on your comment on having more benchmarks on recall. So I'm wondering how those benchmarks will look like. Do we need to, for example, know all the possible correct answers in the universe, or do we need to have a way to check those as a context in for software engineering? There are many benchmarks that use, for example, test cases or specifications to check the correctness of code, new code that's not in the training set at all. Are those considered recall?
Yeah, fortunately, recall of the undiscovered, let's say, quantities is impossible to check without actually doing some work, right? That is that they're running some kind of experimentation. And then that's the reason why one kind of, let's say, interesting area that I think machine learning researchers should move forward more is this kind of active learning and online learning setup, where we kind of, let's say, give up on the idea that the data is already collected in advance. And then we need to think about what is the most reasonable way to collect new set of the data and then verify it, assuming that there are going to be that huge amount of the delays there. So trying to move toward the black box optimization that is scaled up and then is much more flexible than the current approaches. I have another talk about that one, but unfortunately we ran out of time. But yes, I'll try to share something with you by email later.
Cool. Been a great talk and a great set of questions. Let's thank Cho again. A small token of our appreciation. We have a small gift for you. Thank you for coming.
Thank you. Yeah, nice.
Love it. Thank you.
Thank you, everyone.